Alright, hi guys, welcome once again to our channel. Okay, welcome back to Tutor Glycol classes. Alright, from the board you will see simple harmonic motion 2, and I believe you kind of be confused, like, okay, why is there 2 there? Yeah, if you are seeing this video for the first time, especially this particular simple harmonic motion, it means that you have missed out in the part 1. I made a video on the part 1 of simple harmonic motion where I treated all the basic principles on simple harmonic motion. Yeah, so please just go to YouTube, search for Tutor Glycol. You see simple harmonic motion 1. So I've taught part 1. So this is just the continuation. So these are the objective of this video. We're going to be looking at solving questions based on what was taught in part 1. Yeah, I explained the formulas, velocity, amplitude, period, all of these critical aspects of simple harmonic motion. I touched them in the part 1. So in this video now, we're just going to be solving questions because we didn't solve much question on that part 1, or we didn't even solve any question. But in this video, we're going to be solving several questions like that. We're also going to be explaining simple harmonic motion in terms of the simple pendulum bob and the mass in a spring system. That is particularly the period of simple pendulum bob and the mass in a spring. I did some things on that on the part 1 though. We are also going to be looking at energy in simple harmonic motion. We're going to be looking at forced vibration, damp oscillation, and resonance. So this is basically what we're going to be talking about. So if you watch part 1 and you watch part 2 of simple harmonic motion that I made, I'm telling you, you will not have any challenge on any question on simple harmonic motion. So all you just have to do is just go watch part 1, then come to part 2. But if I've watched part 1 before, then definitely you can start part 2. So let's quickly solve some questions. So solving questions based on what we did in part 1. So here I have some questions here on this phone, which we are going to be looking at. I want you to pay attention because I don't want to be writing questions so that it will not take much of our time. So I'm just going to have the questions here and I want you to listen up, okay? So let's look at the first question we have here. Okay, we have an object of mass 0.4 kilogram attached to the end of a spring and is whirled around a horizontal circle of radius 2 meters with a constant speed of 8 meters per second. Find the angular velocity. So first thing, we have the mass. The question said the object has a mass of 0.4 kilogram. Secondly, we have the radius r to be 0.2 meter, to be 2 meter rather. Then thirdly, we have the velocity, that speed, to be 8 meters per second. Find the angular speed. So we want to find out from what I taught you in simple harmonic motion part 1. Remember I said the relation between the velocity and angular speed, v equals wr, right? So if we make w subject to the formula, that's this omega is equal to v over r. What's v? 8. What's r? 2. 8 over 2 give you what? Good. 4 radian per second. So that's the answer. So if they give you a jam question or something like this, just solve. It's just the formula you need, okay? Sometimes they can go ahead and say find the centripetal force. Although I've not taught circular motion, but you can from centripetal force, F is equal to mv squared over r. So you can just impute your m for centripetal force and get your answer. So that's just basically that. Another question says the period of oscillation of a particle executing simple harmonic motion is 4x seconds, right? Sorry, 4 pi seconds. If the amplitude of oscillation is 3 meters, calculate the maximum speed of the particle. That's a question. The period t is 4 pi seconds. Okay, and they said if the amplitude a is 3 meters, calculate the maximum speed. Now remember, if I have to find speed t, if I look for velocity, find v. I look for velocity. If I'm to guess maximum speed, from what I taught you in simple harmonic motion also, recall I said the maximum speed of a simple harmonic motion is, the speed of simple harmonic motion is given by v is equal to w root a square minus s square, where a is amplitude and x is displacement. I explained that, and I made us also understand that this formula is just when the object is actually displaced. Please go and watch part 1 video so that you know what I'm talking about. When the object is actually displaced from a distance, so they give you the maximum speed. I explained the difference between displacement and amplitude, and I told you that there are some cases where displacement and amplitude can be the same exactly. So this is the formula. But then I also explained to us that the velocity is maximum at the center, and at the center or at equilibrium position, x is 0. So the maximum speed is gotten at the center. So the formula will be given as v equals w times a. This is just it. This is the formula for finding maximum speed of simple harmonic motion. I explained that in the part 1 video. Go and watch it. So if this is formula, if I'm to find the maximum speed, I will use W times A. But from this question, they did not give me W, they only gave me A. So I will look for W first. So using the formula that relates W and period, remember we said W is equal to 2 pi over T. Is that not? That's the form. I said it there. Go and watch it. W equals 2 pi over T. Right? So from here, impute 2 pi over, what's my T? 4 pi. Pi will cancel pi. 2 here 1, 2 in 4, 2. The answer is 0.5. So W is 0.5, but that's not what we are looking for. What are we looking for? We are trying to look for V. So impute it there. We have V is equal to W times A. W is 0.5 times, what's A? From the question, A is 3. 0.5 times 3 is what? 1.5 meter per second. That's the answer. So you see that the questions are not difficult. It's when they give you a question like that, all you have to do is just look for, write your parameters. Parameters are those sort of value given to you in order for you to solve the question. As simple as that. So let's solve the next question. These are just random examples that you can find, or random questions you can find in simple harmonic motion. So I'm just solving them how the question can come. Now we have another question here. It says, let me look for another question. What is the period and frequency of a simple pendulum bob that makes 40 oscillations in 35 seconds? How many oscillations? And which n to represent the number of oscillations? 40 oscillations. Then time taken for it to complete is 35 seconds. We are asked to find the period and frequency. What did I show us? We said frequency is what? Number of oscillation over time taken. By period is time taken to complete one cycle. We explained that in the part 1 video. So F is equal to N over T. So simply, what's N? 40. What's T? 35. 5 in 40, 8. 5 in 30. 5 in 35, 7. 8 over 7. Just press your calc. So we simply say 8 divided by 7. That's 1.14. So our frequency is 1.14 hertz. Then remember we said the relation between frequency and period is what? Is inverse. So we say frequency is equal to 1 over T. Or use the formula for period, T over N. They are inverse. You can either say 35 over 40, that's 7 over 8. Or use 1 over T, that's to be 1 over 1.14. Any of them you use will give you the same answer. So pressing calculator, 7 divided by 8, 0.875. So our period, 0.875 seconds. That's easier. Now look at this question. Look at this question. It says a boy timed 30 oscillation N 30 of a certain pendulum bob thrice. So he timed it 3 times. So he did it first time oscillation 30 times in 3 times and obtained 1 minute 10 seconds. For the first time, the time he obtained was 1 minute 10 seconds. The second time when he did it, the time was 1 minute 12 seconds. The third time he did that, the time was 1 minute 7 seconds. Now they now ask us to find the mean period of us. This is a jump question. Option A was 0.14. Option B is 0.43. Option C is 2.32. Option D is 6.97 seconds. So now they want us to find they said the mean period of oscillation of the pendulum is what? What is the mean? So this is very, very easy. Now, the first thing we are going to do here is that they gave us the number of oscillations. Now, this is the question. The boy carried out 30 oscillation. He did it 30 oscillation first time. He took stopwatch. He tossed the thing 30 times. The time it takes the object to do 30 oscillation in the first try was 1 minute 10 seconds. The time it took it to do in the second try was 1 minute 12 seconds. And the time taken in the third try was 1 minute 7 seconds. Find the mean. You know, the mean, the first thing we have to do is to convert all our time to seconds first. So 1 minute 10 seconds is same as this is 60 seconds plus 10, that's 70 seconds. This is 60 plus 2, that's 72 seconds. This is 1 minute 7 seconds, that's 60 plus 7, that's 67 seconds. So the mean time is what? The mean total time. How do you calculate mean in mathematics? We calculate mean by saying sum of all numbers divided by the number. Like for example, if I have 5 numbers and I am asked to find the mean of those 5 numbers, I will add all the cumulative together. I'll add all the numbers together, then divide it by how many numbers present. If there are 5 numbers present, I'll be divided by 5. So after adding them together, so the mean total time of this thing will be simply by adding or mean time. So I'll call it mean time. Mean M time T. That'll be 70 plus 72 plus 67. Or how many times are there? 3. So the mean time is, so use calculator. 70 plus 72 plus 67. 209 divided by 3. 69.67. It will be 209 divided by 3. 69.67. That's the mean time. Now let's find period. So the mean period will not be what? Mean period. What's the way we get our period? Time taken over number of oscillations. Is that not it? So what's the time taken? To be mean time taken rather, since it's 3. Mean time taken over number of oscillations. So 69.67 over 30. So press calculator again. 69.67 divided by 30. That's 2.32 seconds. So 6 correct. So you see, the thing is not difficult. So it's simply like a boy did simple harmonic motion like 30 times, 30 oscillation. First trial, he got 1 minute 10 seconds. Second trial, 1 minute 12 seconds. Third trial, 1 minute 7 seconds. Find the mean period. Mean period means so you have to get the mean time first before you find the mean period. It's the same thing. The only difference is the mean you are hearing there. So it's not difficult. So I'm going to solve another questions. That's some kind of some popular question I have here though. I'm just trying to use those formulas we got from the part 1 video to help you solve some questions here. Okay, look at this question here now. They said the bulb of a simple pendulum takes 0.25. This is a common jam position question that you can see. The bulb of a simple pendulum takes 0.25 seconds to swing from its equilibrium position to one extreme end. Calculate its period. Many students, I've seen this question in jam position. Many students are always confused. The bulb of a simple pendulum bulb, it takes 0.25 seconds to move from one position to one extreme end. What is the period of that simple pendulum? So this is very easy. So this is where the bulb is. This is where the equilibrium position is. So what the question says that it takes the bulb, let's call this a point C. Let's call this extreme end point A. Let's call this extreme end point B. It takes this bulb 0.25 seconds to reach this point here. So from here to here, 0.25 seconds. That's what it took it to reach. This is how many students interpret this question. They always interpret this question so that the time taken for it to go here and back here is 0.25 is wrong. And this is what the question says. The question says a bulb of a simple pendulum move from one extreme end from the equilibrium position to the extreme end in 0.25 seconds. Calculate the period. Now, first thing is, what is period? Period is simply the time taken to complete one oscillation. So the first case here is, let me understand now, what is my one oscillation here? Is my one oscillation time taken for move from this equilibrium position to one extreme end and back to the equilibrium position? No, that's not one oscillation. From here, from point C to point B and back to point C is half oscillation, not one oscillation. One oscillation is when it moves. So let's say it started from here now. So it moves here and back here. That's one oscillation. It starts from this point B. It moves here and back to there. That's one oscillation. But if it started from equilibrium position, one oscillation is it moves from here, back here, to here, and back here. That's one oscillation if it's starting from the center, not just from here to here. That's half. So if we are to find the period, we know already that our period T is time taken to complete one oscillation, right? So let's go. The time taken to complete this one oscillation, let's go. We have from here to here, right? Remember, our one oscillation is from here to here, 1, then from here back to here. So from here to here, 1, from this place back to here, 2, then from here to here, 3, then from here back to this place, 4. You can see. Are you following me now? So this is what we call 1. So if I add a time of 1, 2, 3, 4, that's one oscillation. So the time taken to go 1 is 0.25 seconds, to go 2 0.25 seconds, to go 3 0.2, to go 4 0. So we have 0.25 seconds in 4 places that will give us one oscillation. So we go time 0.25 times 4. Why am I multiplying by 4? Because my one oscillation will complete when it move from here to here. That's 1, back here 2 to here 3, back here 4. I'm multiplied by 4 over how many oscillation? 1. 0.25 times 4. Is that not 2 or so? 0.25 times 4. Okay, that's 1. So that'll be 1 over 1. So the answer is 1 second. So the period is 1 second. Do you understand? So that's how you solve questions like that. The next question we have here is, it says, okay, I've not yet discussed it, but let's listen. It says a simple pendulum bulb that is 0.64 meter long has a period of 1.2 seconds. Calculate the period of a simple. Okay, that's when if I begin to talk about this, explaining simple harmonic motion in pendulum bulb and spring, that's when I'm going to discuss that one. So let's move into, I think I've been able to explain that so far. So what are the likely questions they can ask you? Just a recap from the part 1 video. They can ask you acceleration. Remember, I said acceleration is given by what? A is equal to W squared times what? Times the amplitude. W squared A. Velocity is given by that formula I gave you already. V is equal to W root A squared minus S squared. So these velocities can be this. If they ask to find the velocity of a simple harmonic motion and they give you the displacement and amplitude, use this formula. But once they say find the maximum velocity, you don't need to use this formula again. Maximum velocity, you simply say V is equal to W times A. Are you with me? That's how you get the maximum velocity. Why? We said the maximum velocity is seen at the center. Maximum velocity at the center. Maximum acceleration is at the extreme. If they ask you what is the velocity at the center, they are asking for the maximum velocity. This is it. Are you following me? So we also talk about some relationship between acceleration and angular acceleration, velocity and linear angular velocity. So we talked about all of this in the part 1. So I don't need to go there to make this video long. So let's move to what we have here. Explaining simple. So the next thing we want to talk about is explaining simple harmonic motion in simple pendulum bulb and mass in a spring. So that's what we want to look at now. So basically, one object that helps us to describe simple pendulum. Okay, one object that helps us to describe simple pendulum, that helps us to describe simple harmonic motion is the simple pendulum. And what is a simple pendulum? It's not difficult. Simple pendulum is just like when you take a thread, then you tie it to a bulb, maybe a ball, a boris, whatever. So you take the thread, you hold it like this, then you take the bulb to one side and leave it for it to swing to and fro. So when it begins to undergo a to and fro over a particular time, then we say it is undergoing simple harmonic motion. Exactly. So what I'm trying to say in essence is that when you are asked these questions, you can be asked questions on simple pendulum bulb. So I just want to describe some of the things you have to know about simple pendulum bulb and the mass in a spring. And I think when I begin to talk about the mass in a spring, I'll just explain the energy together with it. I'll be explaining, if I'm talking about simple pendulum bulb now, the moment I start simple pendulum bulb, simple harmonic motion in simple pendulum bulb, I will explain the energy you can see in it together with it. When I entered for mass in a spring, I will explain the energy you can see together. Simple pendulum. So let's say this is my pendulum bulb at the equilibrium position, center, equilibrium. Okay, so this is when I took it to this side so that I can displace it. Then it begins to move to and fro. This is how it is. Okay, so you took it to this side, to and fro. So when it starts from here and it moves to this side, so I'll call this side point A, I'll call this side point C, I'll call this side point B. Okay, point A and B are the extreme position. Take note. Point A and B are the extreme position. Extreme, that means end. My point C is the center. I call it C so I easily remember center. Okay, equilibrium position. So So anytime you are asked to find most questions, maybe the period, they are always asking you to find it with respect to the equilibrium position. Yes. So if I displace this my simple pendulum bob from this point A, it moves to point B and back to point A. It has completed one cycle. If it goes again, it has got 2 cycles. Now the reason why we call it, the reason why I say it is undergoing a simple harmonic motion is because at every given time, it always passes through the center. Is that not it? There is no how this simple pendulum ball will go to B and A without passing through the center. So this is what we call simple. So when an object begins to move through a pattern, passing a particular point periodically, it is not simple harmonic motion. Do you understand? So likely question. So this is a simple harmonic motion. The bulb itself has a mass. Is that not it? It has a mass. The thread. So this is the bulb. This is the bulb. This is the thread. So the thread has a particular length, L. The mass is measured in kilogram, gram, mostly in kilogram. So it has a mass, right? It has a thread, L, good. And if you also notice, gravity, the object is moving. So when this particular bulb is moving towards point B, is going upward. So gravity is acting, so it's making a work done against gravity. So gravity is also acting on this bulb, G. Are you following me now? So the period of this thing, the period of this simple pendulum bulb, we already assigned that period T is given by 2 pi over W from the first video we make in part 1. Period T is given by 2 pi over W. Now, if my bulb, I don't know, should I do that here? Because what I always advise students, see, know the formula. When you know the formula, right, you can easily manipulate. Okay, let me quickly say this thing. The general equation for simple harmonic motion, okay, is given by MA is equals to minus. Should I do that? I'm kind of thinking. This is an O-level video, but that is actually 100 level. You might actually, okay, I'll break it down. Let me not rush. Let me take it bit by bit. Let me just take it bit by bit, because I don't want to go too deep and then all those jam students, maybe something you don't even need in jam, something you don't need in percent. Now bringing it into the video, you're not making you. So let me take it bit by bit. Okay, let me take it this way. So remember, so in this place now, there's an angle between theta, right? There's an angle between my bulb. Like if I draw an horizontal line like this, there's an angle there. So if this my bulb is at point B, remember it's here now, and what I wanted to generate the formula. If you look at your textbook, they just went straight to T equals 2 pi root L over G. And many students don't really know how this thing came from. Okay, this is what I'm going to do. So that I will not waste time in this video, I'm going to make a separate video, like I said, for those who want to, especially those of you in 100 level, or those of that will enter 100 level. I'm going to make a separate video to tell you how they got this formula. Okay, I'm going to make a separate video. Yes, I'm going to make a separate video to show you how they got this formula. So I will not really bulk the thing and make it confused. Okay, so for a simple pendulum, but what I just wanted to know is that T is equal to 2 pi root L over G, where our W here, this is our omega sign. W is root G over L. So G over L. Somebody is already confused. Okay, and this is what I'm trying to say, or this is what I'm saying in essence is. What I'm saying in essence is that the period of a simple pendulum bulb, since there's length and gravity is acting, the period depends. Now, the period of a simple pendulum bulb actually depends on the length of the string, the length of the thread. The shorter the length, the longer the length. And it also depends on the gravity. It does not depend on the mass of the spring. These are potential questions you can see. It does not depend on gravity. It does not depend on length. Sorry, what am I saying? It does not depend on mass. Sorry. Something distracted me actually. It does not depend on mass. It depends on length. It depends on gravity, but does not depend on mass. That's why you see that in the formula you have in your textbook, you have T is equal to 2 pi root L over G. Are you seeing it now? So a question can come, a question, which of the following does simple harmonic the period of a simple pendulum bulb depend on? They'll put length, they'll put gravity, they'll put mass. Some people who include mass is wrong, because if you look at the formula now, you know that there's no mass here. So the period of a simple pendulum bulb does not depend on mass. It depends on the length. The shorter the length, the shorter the length, the faster the faster it will be going. But the longer the length, the short it will not be moving fast. So it depends on length. Then gravity, it depends on gravity, because gravity changes from place to place. Gravity is not constant everywhere. If you go outside the universe, you see that gravity changes from place to place, from one location to another location. Gravity changes. Okay, so because there is a change in gravity and period depends on gravity, so also if you move the period of a simple pendulum of a place like this, if you go to another place where the gravity is different, the period will change. So it depends on length and gravity. So this formula here is actually a formula that is used to find the period of a simple pendulum bob. So they give you the length, they give you gravity, and they say find the period of this simple pendulum bob. All you have to do is implement this formula. Now, knowing that the relationship between our period and angular velocity is given as t is equal to 2 pi over w, knowing that the relationship is given as this, you can also as well notice, you will notice that if I'm to relate these two things, okay, if I'm to relate this, I can rewrite this equation as t is equal to 2 pi times 1 over omega. I can rewrite it like, right, so that by equating them, these 2 pi, we can see this 2 pi, then I will have something as 1 over omega is equal to root L over G. Are you following me now? So if I cross multiply and do mathematics, I will find out that my omega is equal to root G over L. Why am I showing this? There are sometimes they will give you graph, or maybe they will give you a question, they will give you length. They will give you the length of the simple pendulum bob. When they give you the length of the simple pendulum bob, they will say take G as 10 meters per second. Find the angular velocity. Some students will be confused. All you have to do is know that angular velocity of a simple pendulum bob is square root of gravity over length, while period of a simple pendulum bob is 2 pi root L over G. Knowing these things, you can solve any question. Now, there are also some cases, yes, where they will give you variation. They will say if the simple pendulum bob, if the length of the simple pendulum bob if the length is 2 meters and the period of that particular length is 3 seconds, find the length when the period is 2 seconds. That's variation. In a case like that, what do we do? Are you following me? This is potential question you'll be seeing. Students are confused, but it's not difficult. In a case like that, where they give you, now you will simply say, since period is dependent on length and the relationship from the formula t is equal to 2 pi root L over G, we will notice that t depends on length, t depends on gravity. Are you following me? T depends on length, t depends on gravity. So from here, the relationship between t and length is that they are directly proportional. T is directly proportional to the root of the length. Are you following me? T is directly proportional to the root of the length. So from Boyle's law, if you remember Boyle's law, P1 V1 is equal to P2 V2. Why? Say pressure is inversely proportional to volume, right? From Boyle's law, pressure is inversely proportional. So by making your constant and cross, but you have P1 V. Good. So from mathematics now, if I'm to bring in mathematics here, if I bring in my constant sign, I will have T is equal to K root L. Make K subject to the formula, I will have K is equal to T over root L, right? So using the same principle which in Boyle's law P1, so if I will have two conditions, it will mean that my T1 over root L1 first condition will be equal to T2 over root L2, second condition equal to T3, continuously like that. So if they give me a question where they say my first length is L1 and the period is 3 seconds, then find the second length when the period is, this is the formula you are going to use, T1 over root L1 is equal to T2. Or simply, if you cross multiply from here, you find out that T1 over T2 is equal to what? Root L1 over root L2. Are you seeing it now? As simple as that. From here you can solve. So generally, the formula will not change. If I to rewrite this whole formula upward there, I will have T1 over T2 is equal to from solved root L1 over L2. So knowing this formula you have to know. So anytime they give you a question whereby they give you two conditions, if the length of a simple pendulum bob is 3 meters, calculate it, and the period is 2 seconds. Calculate the length when the period is 5 seconds. So first period 3. T1 represent the first period. L1 represent the first length. T2 represent the second period. L2 represent the the first period mentioned in this question is the T1. The first length measured in the equation is the L1. The second period measured in the equation is the T2, while the second length is the L2. So let's look at, that was one of the questions I was trying to explain to us. So let's look at, okay, before I look at that, I already said I will explain energy alongside with it. Okay, so now energy of a simple pendulum bulb, or simple harmonic motion, then please take note that the energy can either be, this is simple pendulum, this is this with height and velocity. The energy can either be kinetic energy or potential energy. And I made a video some time ago. I said that potential energy is the energy that deals with height. Kinetic energy is the energy that deals with motion. So anytime he's talking about height, anything dealing with height is potential energy we are going to refer to. And anytime we talk about velocity, it's kinetic energy. So from this illustration, we notice that at what point are we going to be getting height? It is when the bulb begins to move towards B or towards A. So when the bulb moves towards the extreme position, what do we have? We are dealing with height because it will be moving. Okay, it's going up. So at point A and at point B, the potential energy is max. Don't forget. These are potential questions. Potential energy is maximum at the extreme position. So at what position do we have maximum potential energy? At the extreme position. Why the kinetic energy is minimum or zero? Now, why is kinetic energy minimum? Is because as you move away from the center, the velocity reduces. I explained this in, let's say, if I throw a stone upward, the higher the stone go, the slower it becomes, because gravity is acting against it. So the velocity will be reducing as the object goes up. So as it is going up, it is moving against gravity. So gravity is trying to push it backward. So imagine you're trying to move forward, something is pushing you, your velocity will reduce. So because velocity is reducing, kinetic energy will reduce. So kinetic energy becomes minimum at the extreme position. So at the extreme position, kinetic energy is minimum, potential energy is maximum. Don't forget these things. These are likely questions they ask in exams. Please. Okay, but then if it is moving backward towards the center, so imagine the stone that was going up, that was having reducing velocity. As it begins to come down, what do you think will happen to its velocity? It will increase because gravity is acting down. It's more like an external force is pushing it again. So imagine you are running. As you are running, there's something is pushing you. So your speed will increase. This is why we say the velocity is maximum at the center, because speed is increasing. So at the center, potential energy becomes minimum or zero. Why is the potential energy minimum? Because at the center there is no longer height. Height is becoming zero. So as the object begins to move from the extreme position towards the center, the height is reducing. So potential energy becomes minimum, while kinetic energy becomes what? Maximum. Are you following me at all? So this is it. Oh, if you can follow me, you will not have issue with all these things again. Any question they will ask you on simple pendulum and simple harmonic motion is what I've dealt with. Likely question like angular velocity, find the period in two conditions, find the period 2 pi root. These are the likely questions they will ask. Potential energy, kinetic energy, as easy. So what's the MGH? And there was a video I also did for simple pendulum bulb. Let me just recap that I showed us that the formula is MGL into bracket 1 minus cos theta. I made a video on that already. Search my YouTube Tutor Glycol, you will see the video, or search my TikTok Tutor Glycol, you will see I made the video there. It's there. When they ask you what is the energy in a simple pendulum bulb, the formula I gave from that video was simply the energy or work done against gravity is MGL into bracket 1 minus cos theta. I showed us how this was true in that video. I already made the video, so I will not make it here again because it's kind of longer. Okay, so I made a separate video for that. So just go search Tutor Glycol. It's a 5-minute video, so you will know why the energy is this. So this is the energy. So let's move on. Let's solve a question on this. It says, where's it again? A simple pendulum bulb, 0.64 meter long. So that's L1. 0.64 meter. Okay. Has a period of 1.2 seconds. T1. Calculate the period of a similar pendulum of 0.36 meter. Calculate the period. That's the second period. T2, we don't know it. And the length is 0.36 meter. Right? So we should find the period. So I already explained it now. So what's the formula? We say T1 over T2 is equal to root L1 over L2. This is what I'm trying to say. When they give you a question like this, these are the derive the question from. So what is T1? 1.2 over, what is T2? We don't know it. That's what we're looking for. Root. What is L1? L1 is 0.64 0.64. What's L2? 0.36. So let's see that 0.64 over 0.64 divided by 0.664 divided by 0.36. 16 over 9. This is root 16 over 9. So if I find the square root of each of them by such separately, square root of 16 is what? 4. Square root of 9 is what? 3. So we're having 1.2 over T2 is equal to 4 over 3. Cross multiply and make T2 solve the formula. You have T2 is equals to 3 times 1.2 over 4. So 3 times 1.2 divided by 4. 9 over 10. That's 0.9. So the period is equal to 0.96 as easy. This is not it not take me 3 seconds to solve. Even with the calculator, it did not take me 3 seconds to solve. So, but some students will meet this question in an exam, or they will skip it or pick any answer. But this is how to solve it in case you meet such question in your exam. So now we're going to look at another thing again. And like I said, that as I'm teaching, I'll be explaining the energy alongside with it. So now the mass, I've explained for simple pendulum. Now I want to look at the massless spring. So the spring system. That's what I call it. I call it the spring system. So that's the next thing we'll be looking at. The spring system. Spring system. So the spring system is a system whereby a mass is attached to a spring and is okay, let me just give a diagram. So this is my spring and this is my mass. So you know the spring uses Hooke's law. Remember Hooke's law? I will make a video on that soon. The Hooke's law. Force is directly proportional to the extension. F equals K equal. So before this whole thing, this spring, note that the spring itself, like this is the spring, this is the mass, like this is the body attached to the spring. Okay, so before, without this mass attached, this spring on its own has a mass, like it has its own mass. So if I now attach this mass to it, it will not be like the mass of this spring plus this mass of this whatever object I'm attaching to it. So let me call this thing block. Let me not just call it mass. So it will not look as though I'm talking about something. Let me call it block. So I attach a block to a spring. So the spring has its own mass, the block has its own mass. But then when we are dealing with question of simple harmonic motion with spring or with a spring system like this, we don't consider the mass of this spring because it is negligible. Let's take for example, the block is weighing 3 kilograms, but the spring is weighing 0.0001 kilogram. If I add the two of them together to give me 3.0001 kilo. Is this not the same thing as 3 kilograms? It's not the same. This is why in most questions we used to avoid or we don't used to talk about the mass of the spring. Yes, because it is negligible. The value is too small most time. Like it's too small most time. If you weigh it, you will not really get it. So if I add the mass of the object to the mass of the spring, it will give me the same answer as the mass of the object. So that's why most time we used to avoid the mass of the spring. So we don't need to really look at it. We don't really look at it that much. So, but the most proper way is that when I solve, you're supposed to add both masses together. But the mass of the spring itself is negligible. So just like the way we did on simple pendulum ball, I'm not going to be deriving equation in this play. I'm not going to because there's actually a way that it was gotten. I will make a separate video, especially for those of you who are in 100 level seeing this video and you want to know, because I did it in my 100 level days. Yes, when I was I'm a medical student. When I was in 100 level, I did that. Yes, so I'm going to explain a separate video for you people so that you know how that was gotten. But then that's not where we are going to. So what we are looking at first is the period. Okay, so the period, you can see the difference. So there's a difference between a spring system and simple pendulum. That's how I separated this. So this is a spring system. The period of a spring system is given at T is equal to 2 pi root m over k. This is the formula for a spring system. So using the same method I explained, remember our T is also T is equal to 2 pi over W, right? So if I'm to separate it the same way, I will get my W to be equal to root k over m by inversing what the same thing I did for simple pendulum exactly. So what are the likely questions you can get in this place? They can ask you what k here is the spring constant. Hooke's law, remember Hooke's law now? That k in Hooke's law, that's the spring constant. M is the mass of the block. T is the period, okay? So if they ask you, they give you a spring system, they give you K, they give you M, they ask you what is the angular velocity, which is W. You just say root K over M. What is the period? 2 pi root M over K. In a much similar way, for this spring system, the period depends on mass and the spring constant. But in simple pendulum, it does not depend on. You see the difference now. This is why I'm trying to separate, because there are some questions that will give. Be able to know, is it a simple pendulum or is it a spring system? For the spring system, mass is included. So period depends on mass. Period depends on spring constant. Are you with me now? But in a simple pendulum, it does not depend on mass. It depends on length and gravity. But here is mass and spring constant. So the same way, they can ask you that if the mass of the blah blah blah, you can also make a relationship out of this. And I forgot to say, they can also ask you of frequency, but it's not difficult. Remember the relationship between frequency and period, right? So if they give you a question and say find the frequency, all you have to do is get your period, then say 1 over period. That's the frequency. It's not remember the relationship between frequency and period, that F is equal to 1 over T. As easy as that. So they can ask you question on this, this, and this. And okay, more so, they can also ask you question on energy. So let's look at. So energy is where I am concentrating in the most. But this is what I want to. These are the likely way question can come for you. That energy. They can ask you, what is the energy stored in the spring? See, know these things, because many a time students are confused. You will see many students will cram from your textbook. You already know that. Oh, the energy of a simple harmonic motion is half Ka square, right? Is that not what you cram? Then when you solve some question half Ka square, they say find the energy stored in the spring. You know it's half Ka square. The answer you got, you look at the textbook answer, you see a different. You know, why are they using half Ke square here? But then they said the energy is half Ka square. I will explain to you in this video. These are the likely way they will ask you question. They will ask you, okay, what is the energy stored in the spring? Good. Energy stored in spring. They will ask you, what is the mechanical energy stored, or the total mechanical energy stored in spring? Total mechanical energy. And they can ask you, what is the energy stored in the spring from the point of displacement? There are 3 ways. So it is the examiner that tells you the formula you use. So now, firstly, what do we mean by energy stored in the spring? So this is the spring. It has not started undergoing simple harmonic motion. Now imagine this spring now. The total length, the normal length of this spring from here to here is 5 centimeters. Okay, that's the normal length. Are you with me? So now I took this block, displace it downward. That is this block, and I displace this block to this point here. So an additional length of 3 centimeters has been added, right? Are you with me? I have not started simple harmonic motion yet. I only drag it down. I have not started simple harmonic motion yet. Good. So this new position now is my equilibrium position. Equilibrium. Remember in simple harmonic motion we deal with equilibrium. That is where the balance point or the center point of the motion. If I was now asked what is the energy stored, the energy stored in the spring is the energy with which it undergoes Hooke's law. So by Hooke's law, I've not taught Hooke's law, but you should have prior knowledge. By Hooke's law, energy in a spring is what? Half Ke square. Is that not it? By Hooke's law, half Ke square. So when they ask you what is the energy stored in the spring, it is the energy that is actually stored inside by Hooke's law. Are you following me? Energy stored inside by Hooke's. So the energy I will say now, from this was the initial position, and I extend it to this place 3 centimeters. My E is this 3 centimeters. This 5 centimeters is my normal length. I'm not using that one. Are you following me? Now, but then they now said, oh, and we are going to say a question on that though. They now went ahead and said, an object was displaced, or let's say a mass was attached to a spring and it was extended by 3 centimeters. If the object is displaced 7 centimeters further, so displaced 7 centimeters further from this 3 centimeters, it was now displaced 7 centimeters further. This is where it is now. This is where the simple harmonic motion actually started from. 7 centimeters. So displacement now has been involved, because remember in simple harmonic motion we deal with what? Displacement. It was not displaced 7 centimeters before. They now ask us, what is the total mechanical energy stored? Now the total mechanical energy stored, the formula is half Ka square. 1 over 2 times K times A. A is amplitude. So this maximum displacement is the 7 centimeters. So I'm using this one. Now what am I trying to say in essence is that when they ask you what is the energy stored in the spring? It's just the one before this, just extended using Hooke's law. But when they ask you what is the total mechanical energy in the spring, is the displacement, this 7. So if I want to solve now, for energy stored, I will use E, and this is my extension. For total mechanical energy, I will use A, which is my 7 centimeter. Are you following now? Then if they now ask us that what is the energy in the spring from the initial point of displacement, then I'll say 3 plus 7. So if I'm using E, I'll use 3. If I'm finding A, I'll use 7. But if I'm finding from the point of displacement, I'll use 3 plus 7. That's 10 centimeter. So it is the examiner that tells us what formula we are to use. That's why you see in some cases you see energy is half k E squared. That one is actually asking for energy stored. So when they say what is the energy stored, you use half k E squared. But when they ask you total mechanical energy, you use half k A squared. That's amplitude. But in most cases, examiner, what do they ask you in simple harmonic motion is total mechanical energy. This is what they always ask you in most cases. But why am I explaining this is in case you see this thing, so you will not confuse this one and this one to be the same. And yes, sometimes they can ask you the potential energy, the kinetic energy. Okay, potential energy mg is height, half k is half mv squared for kinetic energy. As simple as that. So these are the likely questions they can ask you under the spring system. Like I said, I'm going to make a different video that explain how all this formula came about. I don't want to make it that too long. So what are those things you have to take note of under the spring system? Take note of the period, 2 pi root m over k. Take note of the amplitude, w equals root k over. I'm not cramming this because I know how to solve. Like I know how to. If I forget it, like I'll just derive it myself. So I don't need to cram it. So I already know them. I know the formulas. All the formulas. I know them. If I say a question, I know what to do and how to go about it. I get what I'm saying. And in much similar way, I want you to know how to go about it. So know these formulas. You can start by learning it on a daily basis. And the more questions you solve, the better the thing will stick. That's how I knew my own. As I was solving more questions, the thing was sticking. As I was solving more questions, the thing was sticking. So let's look at an example. Anyways, this one it talks about touches everywhere. So I'm going to look at it. I'll read the question out for you first. It said a body of mass 500 grams suspended from the end of a spiral spring, not pendulum, a spiral spring, which obeys Hooke's law, produce an extension of 10 centimeter. If the mass is pulled down a distance of 5 centimeter and released, calculate the force constant of the spring. You can see a body of mass 500. So this is it. Let me just draw it. A spiral spring. This is the body. The mass of the body is 500 grams. In kilograms, it will be what? 0.5 kilogram. But because we divide by 1,000. So they now said this mass from the question they said it was extended. Look at it says if the mass is pulled down, produce an extension of 10 centimeters. So immediately they attach this mass to it, the thing now became extended. No, remember, without the mass, it was in the particular position. So immediately they put this mass, like immediately they attach the mass to it, the thing now extend downward. Because of the weight of the mass, it didn't pull it. It's not simple harmonic motion. It didn't pull it down a bit because the thing it has weight now. More like, how would I say this now? More like you put a strong rubber rope. You tie it horizontally, a string horizontally. No, the thing will be directly horizontal when no load is attached. But the moment now place your hand and drag it, what do you think will happen? The thing will come down exactly. So that's what actually happened. So immediately the mass was attached to the spring. Because of the weight of the mass, the spring itself was extended. It became extended a distance of, is it 10 or 5? A distance of 10 centimeter. So it's extend 10 centimeter. This is the extension. So mass is 0.5 kilogram. Extension is what? Is 0.1 meter. I convert from centimeter to meter, divide by 100. So we are asked, the first question says find the force constant. So by Hooke's law, we are looking for K, right? So we know F is equal to KE. K is equal to F over E. But this thing, our force is represent our weight, the weight of the block. So F equals what? Mg over E. What's the mass? 0.5 times 10 over, what is the 0.1? 0.5 times 10, that's 5 over 0.1. The answer is 50 Newton per meter. So our first constant is, which is K, is 50. That's how I got it, mg over E. So I've gotten that first one. Now the second question says the frequency of the oscillation. So I told you for this kind of question, we want to get frequency. First thing you do is get your period, right? So T, what's the period? Pause the video and tell me the period. Good. So the period will be 2 pi root m over k. So that'll be 2 pi. I'll just press calculator directly. What's our mass? 0.5. What's our k? 50. So I'll press the calculator direct and get the answer so that I will not waste much time. So 0.5 divided by 50, square root of answer times 2 pi. That's 0.628. 0.628. But this is not what they asked us to find. They asked us to find frequency. So frequency is 1 over period, 1 over 0.628. So just press calculator. 1 divided by answer, 1.59. 1.59 hertz. So that's the frequency. I told you before that if you want to find, you can ask to find the frequency. When I ask you to find the frequency, find the period, then do 1 over the answer, or 1 over the period will give you an answer. So the next thing they want us to find here is find the period. Okay, I've already gotten the period, so that's as simple as that. I've gotten the period. So the next question was find the period, and this is the period here. Then the next question was find the angular speed. Find the angular speed. So what's the formula for our angular speed? To what? W. I showed us W equals what? Root K over M. Or remember our angular speed is also W equals 2 pi over T. So either use your T to find your this thing, or use K and M to find it. So if you have to use this now to be root, what's K? 50 over what is M? Our M is 0.5. So get it now. So the answer will be, let me just press calculator. 50 divided by 0.5, square root of answer, that's 10 radian per second. And the last one is find, let's say they didn't put I want to add this one. Let's say the question says find the energy stored in the spring. Our formula will be what? E is equal to half Ke squared. So our E is what? This is what we're going to use for energy stored in the spring. But if the question says find the total mechanical energy, that would be E is equal to half times K times half Ka squared. Our A is the amplitude. Yes, it was stated in the question. The question says something. It said if the mass is pulled down a distance of 5, so from this place now pulled down, now simple harmonic motion is now involved. If the mass is now pulled down a distance of 5 centimeters, pulled down, so that 5 centimeters is what we are going to use as our A. Are you getting it now? So this is how we solve questions on simple harmonic. So I believe I've been able to touch some this. And lastly, we want to explain forced vibration, damped oscillation. And so forced vibration, what is forced vibration from the word? But before I explain, let me explain damped oscillation. What is damped oscillation? Damped oscillation simply means when a body is already in simple harmonic motion, then its amplitude begins to reduce little by little because it is losing energy. Like it's a normal procedure of things. Let's use the bell for example. So if I ring a bell, bam, the first sound gives the loudest one. So the bell begins to go on its own. Bang, bang, bang. After some time, the sound will be reducing. Amplitude is reducing. So that's bang, bang. Why? Because it's losing energy. Bang, bang, bang. A point comes, what will happen? The bell dies down. That's damped oscillation. An oscillation where the body's amplitude begins to reduce on its own little by little because it's losing energy. Then over time it stops. That's damped oscillation. And another example is that thing they push now, what they call it in school or in playground, that wheel. The child will sit down, you just push it. So immediately you give it the first push, the thing goes up, come back. The first push gives it the highest height to get to, right? So it goes up, come back. The next height will not reach that first one. And just like that, the amplitude will be reducing. Then after some time it stops. That's what we call damped oscillation. An oscillation where the amplitude is reducing over time because it is reducing energy. So some of the characteristics of soft motion, like the amplitude reduces, energy reduces, or energy is lost. That's damped oscillation. Then we have forced vibration. Forced vibration is a vibration that is produced by an external force, an external periodic force. So you see that wheel on I gave as an example. The reason the thing moved forward was because a force was applied. So when an external force is applied to a body for the body to undergo simple harmonic motion, that's called forced vibration. The difference between forced vibration and this is that as long as that force is there, the body will keep vibrating as long as the force is there. But once you remove the force, the body enter into damped oscillation. You see now, So once you remove the force, that vibration enter into that position. Why? Because after some time it will come to a stop. So force vibration is when an external force is applied. Down oscillation when there is no external force, or maybe just in the initial external force. So that's force vibration. Force vibration is just like when an external thing is applied to it. Then what is resonance? Resonance is now a vibrating body has its own natural frequency. But when an external force is now applied, or an external vibration with its own frequency comes to be applied, a point comes where the external frequency and the natural frequency coincide. At that point, the body undergoes resonance. So what do we? A popular example I can use is you see those people that swim, because resonance gives those people that swim that they stay on a dashing board. So they first jump the first time, the dashing board undergoes a vibration. So a point comes, they'll keep doing that, they'll be timing it. The point where their own jump coincide with the vibration of the board, they'll just lift. It will give them a maximum lift. Or another one again is when you take a tuning fork, a vibrating tuning fork, and as the tuning fork is vibrating, you bring it close to the surface of a table. So the tuning fork is an external one. It has its own frequency. Then the table has its own frequency. So the point where the frequency of the tuning fork coincide with the frequency of the table becomes what we call resonance. So resonance is simply when an external frequency, EF, coincide with the natural frequency. That's just resonance. You can see this is in soldiers marching around a bridge. So because if they are marching around it in the same time, at the same time, they will undergo resonance. A point will come, they will undergo resonance, and the bridge may break. And this is why you see that they always encourage them to scatter, because if they march in the same order like that, it will break the bridge. That's the popular jam question anyways. So that's the difference between force vibration, down to oscillation, and resonance. So we have come to the end of simple harmonic part 2. So if you watch part 1 and watch part 2, I'm telling you the truth, you will not have issue with simple harmonic motion. The only thing you just need to do is go and source for question and use the knowledge you've gotten from this video to solve. Remember, I remain Tutor Glycol. So if you are a student preparing for JAM 2027 with any kind of exam you are preparing for, whether private classes or public classes, we offer them all. Okay, all you have to do is just to reach out to us on WhatsApp and we can communicate from there. The number is simply 07036 59 30 57. Remember, we have a lot of programs on JAM today. And if you are a science student, maybe in secondary school, you are struggling with physics, struggling with chemistry, we have special programs for you that can actually help you. It has helped thousands of students over time, so your case will not be different. Okay, so make sure you subscribe. You are watching this video, subscribe. Please make sure you subscribe so that you will be notified when the next video is made. Thank you for your time. See you in our next video.